Welcome to my talk about counting grapevine berries in images via semantic segmentation. This research was done in the scope of the project Novices. The main goal of it is the reduction of fungicide and pesticides in viticulture through the development of fungal-resistant varieties. We help the breeders to collect phenotypic traits by offering an image-based objective method to monitor the plant performance. In contrast to most agricultural applications, it is not desirable in viticulture to simply maximize the yield. The focus lies in the optimization of yield to ensure that the grapes have a high quality. This is realized with thinning methods, where some grape bunches are removed from the plant to ensure that enough nutrients are available for the remaining grapes. In our project, we want to tackle different grapevine varieties like Riesling, Felicia, and Regent, each posing different challenges. Mainly, we focus on the detection of green berries in front of green canopy, since all varieties are green before a certain point in time. This point is called veraison. The sugar content in the berries rises and they change the color from green to dark. As you can see already from the two left examples, although both images show green varieties, the berries themselves look different, ranging from a dull appearance to shiny berries. Furthermore, we want to tackle different training systems, the vertical shoot position here at the left and the semi-minimal pruned hedge on the right. The vertical shoot position system features only one main branch. The other branches are removed yearly. During the season, the canopy is drastically reduced. The grape bunches are dense and the berry size is homogeneous. Most grape bunches are positioned at the lower part of the canopy. The semi-minimal pruned hedge features a bush-like canopy structure with many branches. The grape bunches themselves are loose and smaller compared to the other system, and the berry size is inhomogeneous. The bunches occur all over the canopy but appear mostly in the top part. Our goal is the correlation between the number of visible berries and the plant performance. One example could be the correlation of the number of visible berries with the expected yield. We acquire data with a semi-automatic plant phenotyping platform called Phenoliner. It consists of a grapevine harvester where the harvesting equipment is removed and replaced with a multi-camera system. The Phenoliner is furthermore equipped with a GPS antenna, which enables the georeferencing of every recorded image. The vertical camera system, here highlighted in light blue, produces vertically overlapping images which cover a whole plant. While the Phenoliner is driving over the vines, we get image sequences which also overlap in the horizontal direction. Since every image is georeferenced and we know the stem position of each plant as well, we are able to select images corresponding to single vines. Here is an example of how a human would solve the task of counting objects in an image. Each berry is annotated with a single dot and the number of dots is counted. The image is an example of one of 120 images which were annotated as reference. In contrast to humans, several methods can handle the problem of counting in images automatically. One possibility is object detection, which produces bounding boxes around each object. We do not get detailed information about the shape of single objects. An instance segmentation provides bounding boxes as well, but gives more detail about the object with a pixel-wise mask. This method is able to distinguish instances which belong to the same object class. Another approach is density estimation, which produces an object count per image by integrating over an estimated density map. This method does not offer further information about the objects beside their rough location. We propose the usage of a semantic segmentation. This method provides a pixel-wise mask, but is normally not able to distinguish between single instances of the same object class. We overcome this problem by adding an additional class called edge. This edge enables the distinction of single instances of the same class. This method provides the same information for each object as the instance segmentation, but is less computational intensive. Our whole pipeline consists of a neural network which produces the berry masks. In a post-processing step, we check geometrical and qualitative attributes of each component and reduce misclassifications. In the last step, we discard the edges and only use the class berry and count the number of objects with a connected component algorithm. The result is a berry number per image. The neural network is an implementation from the Bonnet-Al framework. We use the MobileNet version 2 as an encoder to extract high-level features. The decoder is a DeepLab version 3, which brings the mask to the original image dimensions. We apply the network to image patches and get rid of edge effects with a majority vote. We trained the network on 38 images. Each image was cut into overlapping patches with dimensions of 320 × 265 pixels. The following data augmentations were used: flipping, rotations, and blurring. The resulting dataset consists of 5,700 image patches. We apply 3 filters in the post-processing step to reduce the number of misclassifications. We utilize the prior knowledge that berries are roughly round. In the first filter stage, we therefore compare the minor and major axes of each component. If the ratio is below a certain threshold, we remove the element. In the second stage, we observe the area. Especially at leaf edges, some crescent artifacts appear. By building the mean of the major and minor axes, we get a radius. The area of a circle with this radius is now compared to the actual area of the component. Again, if a threshold is not met, the element is removed. The last step applies a qualitative test. Most true berries are well surrounded by an edge. If less than 40% of the component is surrounded, we remove the element. The application of all filter stages leads to a precision gain of more than 5%. We investigate the results for different training systems. Here you see an example of the evaluation with the manual annotations. We overlay the dot-wise annotations with the pixel-wise masks. Green areas show components where at least one manual annotation was inside the area, meaning the berry was recognized correctly. Black areas are misclassifications, no dot annotations lay within the berry area. Pink dots with a black box around them show berries which were not found by the algorithm. For the vertical shoot position system, we achieve a precision of more than 91% and a recall of 92%. Here you see the same method for the semi-minimal pruned hedge. The berries are scattered all across the image and the berry sizes appear to be more inhomogeneous, showing many small berries. Although the situation is more complex than before, we still achieve a precision of more than 87% and a recall of 86%. Furthermore, we investigate the counting for different varieties. As you have seen in the beginning, although all images show green berries here, the characteristics are different. The Riesling berries are dull and do not reflect the light. On the other hand, berries of the variety Felicia are shiny, showing a reflection in the berry center. We evaluate the counting with R-square plots, which show the correlation between the number of reference berries, here on the x-axis, and the number of berries which are detected with our method on the y-axis. In the plots, each red dot represents a non-overlapping image patch of 320 × 256 pixels. The dashed line would be a perfect correlation of 100%. The solid line shows the actual correlation for each variety and training system. We achieve correlations between 90 up to 98% over both varieties and training systems. To put our method into perspective, we compare our results with 2 other methods, an instance segmentation network and a density estimation network. The instance segmentation is performed with the mask RCNN, which is a popular choice for this problem. The density estimation is a U-Net network. We adjusted the training data so that both networks could be trained with the same dataset as our approach. Here you see a qualitative comparison between the manual dot annotations, which were used for the reference, the output of our pipeline in the middle, and the results from the mask RCNN on the right side. The instance segmentation approach tends to find more than the present berries. To compare the results in numbers, we investigate the R-square plots again, seeing that our method works best compared to the others. The mask RCNN achieves significantly worse results, while the density estimation approach is close to our solution. But to put these results into perspective, we have to keep the networks themselves in mind. The mask RCNN has 20 times more parameters than our network. Therefore, the amount of training data might not be sufficient enough to train it properly. Furthermore, the inference time is 10 times higher than for the other two approaches. The main advantage of our approach over the density estimation is that we are able to reason about the size and shape of the single objects. This is not possible with the density estimation. Up until now, we are able to provide the berry number for a single image. We go a step further and identify grape bunches which are present in the vertically overlapping images. Here you can see example for this case, where an object is highlighted which is present in the middle and the lower picture. The berry count per plant is computed by summing up the berry counts for all single images from the 3 cameras and subtracting the numbers of the matches which were found in respect to the middle image. For this case, the final number of visible berries for this plant is 465. The matching is done by using the berry mask. We join the edges and the berry component to get a mask of a whole bunch. The background is not relevant since we are only interested in the grape bunches. Then we match the patch from the upper image with the lower image. If a match is found, we use the information of the patch where more berries are visible. To make our approach easy to use, we built a graphical user interface which processes a whole folder of images. For each point in time, we have 3 images which are jointly processed for each plant. In the end, we produce a berry number for the whole plant, which is shown by these images. If you have further questions, do not hesitate to contact me.